Oh, so I guess we don't need to connect. Sorry. Hello. Uh, Hello, I'm Adeeb. This is a joint work with Dr. Igo Barata and Professor Gasels. So I'll be presenting on leveraging DOLFINx data-oriented design for GPU implementation. So since Joe didn't have any results, so I have some. So the main motivation is that it's to simulate a focus ultrasound problem, which generates and focuses acoustic waves on the targeted region. So it have a couple of applications. One is drug delivery, neuromodulation, and thermoablation. And the model equation is governed by this nonlinear equation, which is the Westerveld equation. You have boundary conditions, two boundary conditions. One is the absorbing boundary condition, and the other condition for the source functions. And since I'm solving it in the time domain, you have some initial condition as well. So by using finite element method, we can discretize the equation and to this equation. So what I did was I choose some solver design, which is firstly it's fully hexahedral. And this is because, as Joe has presented as well, we would like to use some factorization. And I use arbitrary high order GLR-based Lagrange finite element basis function with numerical quadrature using the same GLR quadrature as well. This, if you are choosing your basis function that coincide with your quadrature points, then you'll get a mass lump scheme, which essentially avoid solving of a linear system. And if you use an explicit time stepping, so you'll avoid solving a linear system. And just bear in mind, even though the capitals are, it looks like matrices, we don't actually assemble those matrices. So the key idea for using when you're using GPU is that you need to pass to the kernel the threads and the number of blocks. So what we did is that we map the number of blocks to cells and the threads, each of these arrows, to the degrees of freedom. Okay. So this is an example of a mesh operator on a when you're using JLL quadrature as well as JLL basis. So you'll end up like a collocation point. So if this is a prototype where I did using number, where you can get the DOF map and the determinant of Jacobian as well. So you're adding contribution as well. So that we are trying to do the same thing on GPUs. So there's the changes are not really a lot. If you notice here, there's no loops anymore. So essentially, you are using each DOF, passing each DOF to each thread, and each entity, which is the cells in this case, to the number of blocks. Okay. And just bear in mind that you need to use CUDA atomic add to prevent any race conditions. So from this, I even though I show the mesh operator, in my application, the most expensive operation are the stiffness operator. So and I ran this roofline plot on a NVIDIA RTX 1000, which is like a consumer grade GPU. And even for a simple change like that, you can get like peak performance on 64-bit float and also 32-bit float. This is using some factorization. We implemented a multi-GPU implementation as well. So if you are using DGX A100, you can get, I mean, for my implementation, with 430 million degrees of freedom, you can get almost perfect song scaling. So this is using just a single DGX A100. That's why you get 8 GPUs. So to test whether the GPU implementation is correct, I have worked on the CPU implementation as well. So essentially, I just compared the two results. So this is an example of a transcranial focus ultrasound problem with homogeneous medium. So you can see that the degrees of freedom are not too big, but on the NVIDIA RTX A1000, with double precision, you can solve these 3D problems in 6 minutes, which is quite good if you compare it to a single node on a HPC system, where I was using 62 Intel Ice Lake CPUs with double precision. And we do a simulation on nonlinear problem as well, which is usually for high intensity focus ultrasound problem. And for this, this is P6, so it requires 430 million degrees of freedom. Using 2 GPUs, I can solve this in 5 hours. While using 14 nodes of Ice Lake CPU, it takes 3 hours. But essentially, if you're using 4, then you can get 2.5 hours. So essentially, if you have a DGX A100, then you should use it. So the next step is we would like to do some kernel optimization. Currently, the one that we have is the result is only for RTX A1000. If we are trying to find and checking whether because for different GPU architectures, sometimes you need a different implementation to fully optimize your kernels. And another thing is that we would like to overlap computation and communication, and end-to-end optimization in terms of the solver itself. And finally, we like to use reduce order models, because the main goal is that we would like to get a real-time simulation, if that is possible. So I would like to acknowledge NumFocus and Mr. Sofia Mahmud, which is my mother, for loaning me the money to come here. Thank you.